this webinar on how to model and manage the energy flexibility of heating systems. We are going to focus on some of the key results from the Resonance project. My name is Trina Sorensen, and I'm here with our speaker, researcher Davud Topalović from the Jožef Stefan Institute in Slovenia. With us, we also have Jesper Testrup from Injet, who will be managing the webinar. Next slide, please. So next, I will hand over to Davud, who will introduce you to the Resonance project and its approach to mobilizing demand-side flexibility management before delving into the management of HVAC system, where we will use the Slovenian pilot as a case. After the presentation, we will also have a Q&A session. You can still also ask any question using the question option in the toolbar of the webinar. It's on the right-hand corner at the top, where you can type in your questions, and we will then go through them after the presentation. Thank you, and over to you, Davud.
Thank you very much, Trina. Can we go to the next slide, please, Jesper? Okay, so hello everybody. My name is Davud Topalović, and today we're going to be discussing something about modeling flexibility and control of the heating systems. Here's the outline of the presentation. First, I will provide a technical overview of the Resonance project. Then we will focus on the heat pumps as our flexible resources within the Slovenian pilot. We'll see what are actually the requirements for making a heating system flexible, the architecture of the Resonance of the resource manager, and how we develop the models. Then we will cover a one worked example where a heat pump resource manager is built for one building, its model and the optimal control built on top of it, and then I'll finish with the main conclusions. So here's the brief motivation behind the project. We know that the integration of renewable energy sources into the grid, such as solar and wind, complicate the grid stability and reliability. And one promising solution for this issue is the demand-side flexibility, which is a framework or approach that utilizes the flexibility of the resources on the demand side for balancing the grid and also unlocking the full potential of the renewables. However, the problem is that there's a lack of the common software framework for modeling and connecting these individual demand-side resources. And Resonance project addresses this exact problem, where it builds a plug-and-play software framework for demand-side flexibility management. And to see how it works, let's look at the architecture of the Resonance. The Resonance approach organizes the whole chain from the energy markets all the way down to a single device in the home into a modular, standard-compliant software building blocks. As you can see in the architecture on the right side, there are three main blocks arranged in a top-down hierarchy, and they correspond to three different catalogs that the Resonance is developing. On the top, we have the aggregation and market integration catalog. Then we have the customer energy manager catalog, and at the bottom we have the resource manager. So let me go briefly over each one and describe it. At the very top is the aggregation platform, the market-facing layer. Through its market interfaces, it connects to the outside world, including the energy markets, the DSO, and reserve and balancing power markets. Its main job is to pull the flexibility of many households and buildings and turn it into something it can bid and sell to these markets. And in return, it sends the load management signals, implicit or explicit signals, down to each home, and thus intensifies the flexibility control. One level down, we have the customer. On the customer side, there lives a customer energy management manager, the CEM, or as we call it, the CEM. It is an intelligent software agent that lives on the customer premises in the home or building, and its job is to manage the smart appliances on behalf of the customer to maximize their benefits, typically by minimizing the energy cost while also offering the flexibility to the grid. The CEM uses price signals from the markets and aggregators, and through its automated flexibility management tool, it decides actually how to operate the connected flexible devices. It talks upward to the aggregators and markets and downward to the resources. But the important thing is that it never talks to device directly. That's the job of the resource manager that we have at the bottom. A resource manager represents one flexible resource, for example, a single device like a heat pump or battery. And the pure role of the resource manager is to turn a physical device into a controllable, predictable, flexible resource that the SAM can plan with. To do that, the resource manager has to include components such as the resource model and optimal control model, which are then used to provide the information to the SAM, such as the baseline power forecast or flexibility it can offer. Anyway, in the rest of the presentation, we will focus, our focus will be on the development of the resource manager or a heating system. And given that the main body experimentation behind this development that will be presented here comes from the Slovenian pilot, I will introduce briefly first the Slovenian pilot. Okay. Yeah. So here is the summary of the Slovenian pilot, the summary of the residential households with flexible resources. Together with the industrial sites and network level batteries, a big part of the Slovenian pilot are the residential single family households. Specifically, we operate with 5 households in total, where each household is equipped with different flexible resources. For example, each household is equipped with an HVAC, specifically the heat pump. 3 households have also the PV rooftop, and 2 households have EV charger, and 1 household also has the battery. Now, the main and key flexible resource that we're modeling through the project on the residential side is the heat pump. On this table here, you can see the brief, the summary of the main characteristics of the heat pump, of the heat pumps across the households. We have 1 Bosch heat pump. The other heat pump are of type chronotherm heat pump. They're mainly air to water heat pumps. 1 heat pump is the ground to water, and they come in different capacity, number of heating circuits, and different heat emission systems. Now, the Slovenian pilot through the project primarily supports the use cases that focuses on the implementation and validation of the automated implicit demand response program, which covers objectives and use cases such as the lowering operational costs or increasing consumption, peak shaving, load shaving, etc. So in order to actually implement these use cases, we need to turn our heat pumps into flexible systems by developing the heat pump resource manager. So I apologize for the lag. Let's see if this works. Still seeing the Slovenian pilot. Could anyone switch maybe to the next slide because I'm having a problem? Okay, yeah, the next slide. So before we build anything and delve deeper into the modeling, let's first get the intuition on what does it actually take to make a heat pump or heating system flexible. There are 2 main enablers of the flexibility for the heating system. The first one is the control through the actuators. So we need to be able to control the heat pump. In practice, this is remotely through the actuators such as the thermostat set points. But the control alone isn't just enough. We also need to predict what that control does to the heat pump, specifically how much the electrical power the heat pump will draw for a given control point. Without that, we can move the consumption, but we cannot really plan it. The second enabler is the storage. A heat pump on its own cannot really store the energy. But what it can do is it can use the building itself as a thermal storage. The building mass is represented or acts as a buffer where we can preheat or consume more now and heat less later. And this ability to shift the energy in time without breaking the comfort is the real enabler of the flexibility. But again, to use this flexibility, we have to model it. We need to know how much energy is stored and how it evolves in the building. And the practical measure of that store energy in home is simply the indoor temperature. So to wrap it up, the flexibility isn't free. It has two requirements, and each one comes with a modeling task. The first task is modeling the power as a function of control, and the second task is modeling the thermal state of the building. And this is exactly what a resource manager of the heat pump must provide. Okay, next slide, please. Yeah, so here's the high-level architecture of the resource manager of the heat pump. Okay, I'm having animations here, so this might be a bit problematic. Let me see. So yeah, we'll go without the animation. So on the left side, we have the optimizer, whose role is to implement and run the optimization algorithm. Optimizer does the planning, and therefore, based on the use case of the optimization, it can receive inputs, various DR signals such as electricity price, network tariff, PV generation, etc. On the right side, we have the heat pump. We have the model that represents this coupled system of the heat pump and the building. And now, because of its complexity, this model, the whole model is divided into multiple different components. The first component is a control model, which maps the available controls, for example, the thermostat, into the realized thermal power or heat power of the heat pump. Then the second component is the temperature model. The temperature model maps the realized heat power into the temperature states or the thermal states of the control system. The third component is the coefficient of performance model, which estimates this performance coefficient in order to predict the power demand, to predict this power demand. So the optimizer essentially here uses the model as a simulator in order to optimize the operation of the heat pump. At each operation, it proposes certain control inputs, which are then evaluated by the model and fed back to the optimizer, which then calculates the constraints and the criteria function. Okay, we should go to the next slide. So in order to develop the resource manager, we need to develop each component, from the optimizer to the components of the heat pump model. And when it comes to the model development, the whole process can be divided into three stages. The first stage is acquiring the identification data. This can be one of the most challenging parts, especially in the early phase of the commission. The normal operation data, usually that comes from the household, is not really informative and rich enough for model training. Therefore, we need to perform certain control experiments to excite the system dynamics enough and thus obtain the good data. For example, here I show the data from one day for 2 households for the normal operation, which represents a poor identification data. We can see that the oscillations, we can see these frequent noisy effects and relatively stable heat power represented with the brown color here. And of course, the set point is set to the constant value. So this data, training the model on such data does not guarantee a really good model. So what we do is we apply these control experiments in order to excite the system. Specifically, for example, we turn off the heating for certain hours, let the temperature drop, and then turn it back on and let the temperature rise back to its initial value. Then once we acquire this kind of data, with this kind of data, we can proceed to the model training and validation. For example, here, this slide shows what we actually achieved and conducted during the phase 2 of the Resonance project. We applied over 100 these control experiments over 3 households, where each of these experiments involved certain modification of the set point. And with this kind of data, we are trying to see and identify the data requirements and the requirements of the control experiments for the model identification. Now, the second stage of the model development is offline training of the models. Here we do some analysis of different modeling approaches and structures. The most common type of the models that we use are physics-informed machine learning models, which represent a hybrid approaches that combine physics laws with the machine learning. An example of these models are RC models, linear state-space models, nodal ordinary differential equations, and nodal state-space models. These are essentially physics-inspired models that use machine learning for the parameter identification, right? And whenever we have some kind of dynamical system, we will use such kind of model to approximate the dynamical system. The second type of the model that we use are the pure machine learning models. The most frequently one that we use are autoregressive models with exogenous inputs, neural networks, and also these assembled models, where the one that we use mostly is the XGBoost. Now, once we train the models offline and test different structures, we then proceed to this third and final validation stage of the model development, which is the online validation of the models. Here, we deploy the models for the optimal control and thus further validate them. Now I will go and present one specific worked example of the heat pump resource manager for a 1P8 EE building from the Slovenian pilot. The P8 building is a single family household located in Celje region of Slovenia. It's equipped with a ground source heat pump, PV, and a battery. And the only available control of the heat pump is through the thermostat set point, right? So we don't have any, actually, for any kind of, for all our heat pump systems in Slovenian pilot, the only control available is through the thermostat set point. Now, for this specific use case that we're going to present here, we make some assumptions. The first assumption is that the only available flexible resource is the heat pump and the whole electricity supplied from the grid. So we assume that the building doesn't have a PV. We also assume that the building is on a dynamic retail contract, which means that it is built based on the hourly electricity price. We also assume that it is enrolled in an explicit demand response program, which means that it can receive certain flexibility requests from the aggregator. Now, the way we present the results on the resource manager development comes into two parts. First, we presented the model, and then we'll present the optimizer on top of the model with one optimization use case. So here's the summary of the model that represents this heat pump building resource model. If we recall from the architecture, this model involves three different components: control model, temperature model, and the COP model. Now, in this specific use case, we're actually using one enhanced type of the model to model both control models and the temperature model. And this type is called physics-informed nodal ordinary differential equations. As a control input, it takes the thermostat set point, and also as a disturbance input, it takes the outer temperature and solar irradiation. The model from these inputs then outputs three things. The first one is the heat power, then the indoor temperature, and the supply temperature of the heating system. You can see the structure of the model in this picture here. It basically presents a hybrid combination of the linear state-based model, which models the temperature or the thermodynamics of the building, which is first trained and then frozen, and then we froze the weight of the linear state-based model, append the neural network to it to model the dynamics of the thermostat state, which is then used to estimate the heat power demand of the building as a function of the thermostat set point. So with this hybrid approach that combines the physics and machine learning into this physics-informed nodes approach or framework, we managed to solve both modeling problems with one approach. The third model that we had to develop is the COP model. Here we use the XGBoost model, which as an input takes the supply temperature, outdoor temperature, and the soil temperature. Interestingly here, the big correlation with the coefficient of performance of the heat pump has the soil temperature. And it's very logical because it's a ground source heat pump, which means that it extracts the heat from the soil, from the ground. So this high correlation doesn't really surprise us. And the output of the model is the COP, this coefficient, which we then use to estimate the power demand of the heating system. Now here I show the predicted workflow of one model. Specifically, we show open loop 24-hour ahead prediction for rolling horizon. In the top panel, we can see the inputs with the full red line. The full red line represents the thermostat set point. We can see that from the 10th February 26th to the 13th February, we actually performed a lot of these modifications of the thermostat set point in order to validate the model and do certain experimentation. Anyway, the thermostat set point together with other disturbances are mapped first with this neural network controller to the heat power, which is here represented with the orange line. With the black line is actually the measured heat power response that the heat pump actually achieved. And we can see that the model predicts quite well. It manages to capture this thermal the thermal power response as a function of the fluctuating set point. Once we have predicted the heat power, right, we then go to predicting the indoor temperature and the supply temperature with the linear state space model. Again, we can see that the model predicts quite well the temperature decrease during this off heating period and also the rebound phase during the increased heating period, right? And also the supply temperature is captured quite well. And then once we get the supply temperature and the heat power and also the outdoor temperature and the soil temperature with the COP model, we can finally predict the power demand. Again, we can see that the prediction of the model is quite good. To put this into numbers here, but I'm not going to go too much into details here. Here we show the mean absolute error for each of the 4 forecasted variables. We compare the 1 step ahead and 24 hours ahead performance. For example, for the indoor temperature, we can see that the 1 step ahead prediction is almost perfect, right? The model predict the mean absolute error is 0.02 across across the train validation test set. On 24 hours ahead, the median error is the 0.27. For the train, 0.29 for the test set. We can see some larger distribution on the test set. And also the other targets are have quite well performance. For example, the electrical power, when we forecast the 24-hour ahead, we can see that the mean absolute error is only 132 watts, which is around 0.13 kilowatts, right? And this is on the train set. On the test set, it's even less. So given that our heat pump operates up until 2 to 3 kilowatt, 2 to something like that, 2 to 3 kilowatts, this error is quite good. Okay, now that we have developed the model end to end, which maps the set point to the power, we proceed to the optimal control, to modeling the optimal control, that is the optimizer, and covering one optimization use case. So the role of the optimizer here is to plan the operation of the heat pump. And in order to do that, the optimizer actually has to implement certain optimization algorithm, right? And families of the optimization algorithms that we consider during our research are gradient-based or mathematical programming methods, which can include linear programming or mixed integer programming, quadratic programming, which are all classical MPC methods that require a convex and differentiable model. They're quite good. They, in case given that we have a convex and differentiable linear model in terms of the decision variables, they can guarantee the optimal solutions. They're extremely fast, but they are quite limited to these to the type of the model that we can use for the plant. The other type of the optimization methods are the gradient-free methods, and usually here we use the population-based algorithms, such as the genetic algorithm, NSGA, and the particle swamp optimization. Also, another method that's quite popular, but we didn't investigate it much, is the learning-based or the reinforcement learning. Simply because the reinforcement learning usually requires a lot of good scenarios in order for the approach, the optimization to converge and to optimize well. So in our choice, where our model is not actually convex, it uses the XGBoost in it, right? It's anti-differentiable. We're using, for the optimization use case that we'll present here, we're using the genetic algorithm, specifically this NSGA2 solver, because it supports both single and multi-objective problem cases. And as I already said, it fits really well to our nonlinear, non-convex model. So the optimization use case that we will present here, it is based on two DR signals. So we assume that there are two DR signals which come to the resource manager. The first one is the electricity day-ahead price, which is the implicit demand response signal, which you can see here with the purple color. The other is the explicit demand response signal, which represents the upward flexibility request of 1 kilowatt from 10 o'clock in the morning to 3 o'clock in the afternoon. So this is one explicit demand response signal that the customer energy manager, or in this case, the resource manager, receives and tries to optimize according it. And why choosing this example? This example actually reflects the high local PV production during the solar peak hours, right? Between 10 and 3 o'clock approximately. So the aggregator will recognize this and send this kind of signal to the individual households in order to motivate or incentivize the higher consumption during this high peak solar production. So we know that the role of the heat pump resource manager is to optimize the operation based on these two signals, and it should actually provide the estimate of the available flexibility. Now, given that here we have two objectives, we have two driver signals. This optimization problem is formulated as the multi-objective optimization with two objectives: minimizing the operational costs and maximizing the DR target. So we want to minimize the electricity cost based on this electricity price signal, and we also want to maximize the power consumption based on this DR signal. The optimization horizon is 24 hours, and we operate on 30-minute resolution. The optimization is also constrained, where the hard constraints are imposed on the indoor temperature. So, for example, the customer energy manager sends these comfort bounds to the resource manager, and then resource manager informs the optimizer about them. As I said, the optimization solver that we use is the NSGA2. Okay, now we'll go to the results of this optimization. Let me just switch to the next slide. I kind of lose the control. Okay, so here's the result of the NSGA2 optimization. For optimization setting with the population size of 300 and 100 generations, the optimization converged to a Pareto frontline, including 44 feasible non-dominated solutions. You can see this Pareto frontline represented with the red crosses right here. Here is the zoomed in picture. We can see that actually the convergence is already observed at the generation 15. So this is actually the objective space where each dot represents one solution of the optimizer at the given generation, right? With the blue cross line here, this blue cross line represents the objectives of the baseline power consumption. So we can see that the Pareto frontline efficiently manages to minimize the objectives relative to the baseline consumption. But now, given that we have 44 feasible solutions, the question arises: what kind of solution can we pick from this Pareto font? And we discuss that in the next slide. Okay, so first we will discuss a first extreme solution, which is the solution that has the best cost, the solution that minimizes the electricity cost the most, right? Here on this panel, you can see the Pareto front with the gray crosses and the line, and this is the corresponding solution in the objective space of the corresponding point of this best cost solution. On the right-hand side, you can see the optimal schedule or optimal operation that corresponds to this solution. With the dashed blue line, here we can see the power consumption, and below we can see the indoor temperature, and with the black line represents the thermostat set point. Looking at the pattern of the consumption, we can see that the optimizer for this solution pushes the power consumption, the heating during this region of the low electricity cost, right? Then it tries to track a bit. It tries to also increase the heating during this valley. These activations here that happened actually are because of the thermal comfort. We can see that here the temperature starts to violate this thermal comfort bound defined here with the green region. Therefore, the heating activates. Now, if we want to turn this into numbers, we can see that this solution relative to the baseline solution actually decreased the electricity consumption by 55%. And in terms of the total energy consumption, the optimized solution, actually improved or decreased the total energy consumption by almost 25%, which is quite good improvement. Now we go to the second extreme solution, which maximizes the DR dispatch right away. So again, on the right, on the opposite side, here we have the other solution, which has this best DR dispatch, or the lowest error on following the DR target, right? On the right side, we can see the pattern, and indeed we can see that the full consumption that the heat pump tries to follow this demanded DR target, this 1 kilowatt between 10 o'clock and 3 o'clock. Regarding the other consumption is pushed to this low electricity region. And again, we can see here that the thermal comfort is not violated. The temperature stays in its predefined comfort ranges. Again, if we want to put this into numbers, we can see that this optimal solution delivered exactly 5 kilowatts as it was requested. Although we can see here some variation, we can see some oscillation variation here, which means that the power consumption doesn't always have a straight kilowatt right here, and this is actually due to temperature increase, and then the COP increases and the power consumption decreases. The good thing is that also the electricity cost based on relative to the baseline consumption also for this solution decreased by 34%, and also the total energy by 15 point almost 15.5%. Now the question is what kind of solutions to pick, right? We got this set of flexible non-dominated solutions. And this is actually one advantage of this optimization, where the optimization provides a set of flexible solutions into a single solution. This feature of such kind of optimization algorithm allows the resource manager to define a region of acceptable subset of solutions based on certain specific criteria. And thus it can provide, for example, a power envelope prediction. So, for example, here, we can see this shaded area that's moved a bit. The resource manager can, based on, let's say, based on the requested DR dispatching target, can define this region of flexible solutions, right? And then the resource manager, instead of providing just one solution, can provide the whole set of solutions, eventually providing the power envelope, which can then later be turned back to the customer energy manager, or the resource manager can just pick the most optimal solution according to certain criteria. And for this power envelope, or this favorable region of solutions, we can see that the cost, varies between 1.44 and 1.63 euros, and the target and the DR target is from 0.8 to 5 kilowatts. So that's it about this result. Now to finalize with the conclusion. So here we have demonstrated the requirements for turning a heat pump into a flexible resource. We presented the architecture of the heat pump resource manager, and we showed with a worked example how one implementation of the resource manager for one building looks like. Besides this building, also the same architecture of the resource manager of the heat pump is deployed across all 5 households, all other 4 households, 5 households in total in the Slovenian pilot. Of course, with a difference in the modeling solutions, right? Actually we use different kind of models, variation of the models, and we calibrate the solution to each building. Beyond this example, we're within the resonance project, this modeling solutions that we developed for the Slovenian pilot use cases have been also replicated in other pilots. For example, the supermarket building in the Finnish pilot and single family households in the Greek pilot. So, for example, the nodal ordinary differential equation model that we developed for the Slovenian household can perfectly be replicated and used for the supermarket building in the Finland, or for the single family household in the Greek pilot. Now, the ongoing research that's part of the project and part of our study in our lab at Jožef Stefan is that we're doing this data efficient modeling. We're exploring the data efficient modeling solutions, right? We don't want to always depend on these control experiments, so we're more pushing into this direction to identify what kind of modeling solutions can we use with the minimum data requirements and with the minimum experimentations needed. Also, we're developing and testing the optimization algorithms. We deployed the MPC algorithm on 2 households this winter and tested it. It turned out that it's not an easy task to do, so we're testing the robustness of this optimization algorithm. One, let's say, not disadvantage, but hard thing is that when you test something on the real system, you have to wait for the winter, and you're very limited with the time that you have for the testing. And all the communication, you have to be very lucky. You need to have a good friendly users that will allow you to run experiments on their heat pumps, etc. So that's kind of the process. And also more related to the project, we're also testing the control types for the heat pump defined by the S2 control interface. As I said in the introduction, the resonance framework uses the S2 control interface between which is basically a layer between the resource manager and the customer energy manager, right? And in order to develop such solutions, in order to stick to this common interface, we also need to align the optimal control of the heat pump according to this S2 control interface. So that's it from my side. Now we can go to the Q&A session.
Thank you, Davud.
Thank you very much.
Yes. So there's one sort of general question as to what would it take to replicate the model to into a new setting?
So what would it take to replicate the model into a new setting?
Yeah.
So basically just the data. For example, the physics-informed nodal ordinary differential equation model that we presented here, it uses the thermostat set point as an input, outdoor temperature and solar radiation, and that's it. 3 input variables. So in order to replicate on some other building heating system, we would need this data. But of course, the spectrum of the model that we develop, which can take different modeling, which can take different features, right, and different inputs, is very wide. So I would say that we could definitely replicate it. It really depends on what kind of data, of what kind of sensor measurement does the system provide.
Thank you. Are there any other questions? No other questions? Okay. Well, thank you for listening. Thank you, Davud, for your presentation. Tomorrow we will have another webinar, this time on the importance of a standardized approach to demand-side flexibility. It will start at 11, run from 11 to 12 tomorrow. You can find more information on our Resonance project website, and also all our webinars will be available on the website, available on demand. So thank you and have a nice day.